Okay, hello everybody. Here's Mike here again. So I'm doing a kind of an interview demo with Camp. Um, so Camp, kind of introduce yourself, who you are, kind of some of the cool things you're doing, and maybe do some quick demos of your robots.
All righty. My name's Camp Peavy. I've been building robots for almost 40 years. I'm not a formally trained engineer. My degree's in marketing. If I had graduated on time from Florida State University, I'd have gone to selling advertising sales with the local newspaper. My life would be much different. But I graduated 2 years late. The last project I did was on Apple Computer. They were going public and coming out with the Apple III, and I thought, oh, that looks interesting. I'd like to get involved in that. And so I hired on with the local Radio Shack Computer Center, at which point I decided that I wanted to take this computer thing to the nth degree, as far as it'll go. And it dawned on me that mobile robots are basically computers with eyes, arms, and legs. So I picked up a book by David Heiserman, How to Build Your Own Self-Programming Robot, in 1984. The book was published in 1979, and it changed my life. David Heiserman described an 8085 microprocessor controlled device that you program one bit at a time, and had a 12-bit address bus, an 8-bit data bus. You'd punch the load button and you program it in binary. Now, after about 5 years of working with this graduate level program, I finally created, he had 3 levels of machine intelligence, which is really advanced for this day and a relevant concept for today. He had 3 levels of machine intelligence Heiserman enumerated. With a differential drive system, you've got 9 possible motion patterns. Left wheel forward, left wheel reverse, right wheel forward, right wheel reverse, clockwise, counterclockwise, forward, reverse, and stop. The only 2 motion patterns with any magnitude or displacement, though, are forward and reverse. Okay, and so the level 1 machine intelligence, the robot would make random motions until it discovered one of the motion patterns that has magnitude, and that's forward or reverse. Otherwise, it would consider it a stall. Okay, and so the beta level had an element of memory, where when it was in a particular motion pattern and it tried something, if it was successful, it incremented its confidence level. If it was not successful, it decremented its confidence level, so that when the robot was turning clockwise and then went forward, the next time it was successful moving, the next time it was in clockwise and it tried forward, it tried the successful response, it built up its confidence level. The third level of machine intelligence, generalized, where when it was in a particular motion pattern and it stalled and it didn't have a high confidence level response, it would try other high confidence level responses before finally reverting back to random motion patterns. I've since rebuilt that David Heiserman robot using an Arduino, and I'll demonstrate it later in the program. In 1986, I got a big bonus check for selling TRS-80s to a local community college, and I packed my bags and moved to Silicon Valley seeking great wisdom and adventure. I hired on with Zach Electronics. I was selling electronics. I'm selling computers, but I'm building robots as a hobby all along. I always led with, I'm a robot builder. I build robots. And so eventually, I got laid off my nice cushy network admin job at Intuit. This was 1995. I got a decent severance package, and it's like, what are you going to do with the rest of your life? Well, odds are you'd go back to being a PC tech or a network administrator, but I came to Silicon Valley to build robots. And so I produced this kit called the Protobot. And I wrote an article for Servo magazine. I'm proud of myself. I sold a couple of dozen of these kits, but I quickly realized I'm not going to make a living doing this. But what it did is it allowed me to pivot. I hired on with Jameco Electronics, who had just acquired Robot Store at the time. So I was like the robot guy at Jameco Electronics. I went back to school, College of San Mateo, actually took some electronics classes. That was an eye-opener. And I eventually found my way to a little startup that no kidding, was located right across the street from my house, called Home Robots Incorporated. That eventually became Nito Robotics. And I spent 13 years at Nito Robotics as a robot technician. And now Nito has sold millions of floor cleaning robots. It features a LiDAR, and I've got a Ross hack for the Nito bot vac using the LiDAR, and I'll demonstrate that later in the program too. Since COVID, I've proposed to my sweetheart, and she said yes. So I've moved back home to Tallahassee, Florida, and I'm working on a book. It's called Homebrewed Robots, and it'll basically tell my Silicon Valley story. And I'll have 5 robot projects: the Tablebot, Machine Intelligence, Robo Magellan, Nito Bot, the Nito Turtle, and finally the Smart Table. And I'll show you my Smart Table prototype at the end of the program.
So real quick, before you get into demo your robots off and stuff, talk about how you got involved in Robo games, because I think you were there the first year. I don't think I was there the first year. I think I missed the first year. But,
the highlight of my life was winning the 1996 Autonomous Robot Wars Championship. Hang on a sec.
Okay. So I think David says I was there the first year, but I don't believe I was there the first year of Robo games. But
this is a Robot Wars trophy.
Right.
And Robot Wars was the precursor to Robo games and BattleBots.
Right.
The great thing about entering the autonomous division is you're one of 2. So you automatically make it to the semifinals. And with a little bit of luck, I was up against a fellow named Bob Gross, had a robot named Smart Spike. And of course, there was all this radio control, bash 'em, crash 'em. But with the autonomous division, you were given an infrared beacon that was placed on your robot. And my robot, Gladiator Rodney, had 2 television remote control receiver eyes. And when the left eye saw the beacon, the right wheel would go forward. When the right eye saw the beacon, the left wheel would go forward. When both eyes saw the beacon, it would lower its flipper and charge into the opponent. Now, Smart Spike got caught up on some of the traps out there on his own. Nothing I did. Here's Gladiator Rodney turning in a slow counterclockwise circle looking for the beacon. The crowd's kind of going, huh? After all the crash and bash and radio controls, here's the autonomous division, and it doesn't appear to be too much action. But my robot detected that beacon. It started meandering towards it, lowered its flipper, and I'm going crazy. Yes, because I spent a whole year for this 5 minutes, okay? Right. And ran into Smart Spike, and that was kind of the end of it. At which point I went to Mark Thorpe, the founder of Robot Wars, and I said, well, who won that fight? He said, well, it really wasn't much of a fight. I said, excuse me, I didn't do it, but Smart Spike was disabled, and I did manage to mount an attack. He said, okay. And they gave me the $250 and the trophy, and that's the highlight of my life.
Cool. So was your first Robo games 2004?
Well, whatever the first Robo games was, yes, it was. I also participated in Robo. There was an event in Southern California that wanted to do BattleBot, but yes, and I worked with David Calkins, and I basically ran the Robo Magellan event for years. And also with the Homebrew Robotics Club, we have a popular tabletop exercise we call Tablebot. A Tablebot is a robot that survives, lives, and plays on the table or pays the price. And we do that in 3 phases. Phase 1 is build a robot that goes from one end of the table to the other and back. Phase 2 is to push a block off the edge of the table. And phase 3 is to push the block into a shoebox mounted at the end of the table. And that's a Robo Games event also.
Cool. Can you talk about Robo Magellan real quick about, I mean, I know we've talked in the past about it, and we talked a little bit before they started recording, but can you kind of talk about Robo Magellan? Because it was actually a very popular event. There was a lot of interest in that.
Sure. Robo Magellan oriented with the Seattle Robotics Society. And basically, you traverse like 100-yard playing field. It's got obstacles, curbs, benches, trees. I mean, it's just a natural outdoor environment. And you're basically given a GPS coordinate, and a 19-inch OSHA orange cone is placed on that GPS coordinate. Now you've got bonus cones along the way that your robot can elect to touch before it gets to the goal cone. And what that gives you is a fractional multiplier. Depending on the difficulty of the bonus cone, the lower the fraction, okay? And so, but if you don't touch the goal cone, your score is your distance from the goal cone. Okay, so if you elect to touch bonus cones along the way and you miss the goal cone, it's all for naught. It's kind of like, you know, your robot goes to the planet and, you know, gets the rocks and burns up on reentry. It's all for nothing. So you got to touch the goal cone to take advantage of those fractional bonus cones that decrease your overall time. Okay, and then you're scored on time. Now, the third highlight of my life was getting a bronze medal in Robo Magellan in 2012. My robot, Blue Dog, didn't even have a camera on it. Okay, and I was telling you this earlier. Robo Magellan is not really that difficult because you're given a GPS coordinate. You've got a GPS on your robot. If you simply subtract your target latitude from your actual, if your target latitude is higher than your actual latitude, you need to go north. If your target longitude is higher than your actual longitude in the northern hemisphere, you need to travel east. So now you've got your bearings. You know what direction you need to go in. You can go in that direction and build in some avoidance obstacle routines so that if you reach an obstacle, you back up, you know, 5 feet, turn 30 degree, go forward 10 feet, that kind of thing. You can actually crab around like a 40-foot obstacle, a fence or a curb or something.
Right.
And you will eventually get to your target GPS coordinate. You know, if let's say you're not making any progress with the combined coordinates, just work the longitudinal coordinate, just work the latitudinal coordinate. Eventually you'll get to that coordinate. Now that gets you in the ballpark 10 or 15 feet from the actual cone, but then you have your camera guide you into the cone. But in 2012, I couldn't believe it. It's like hitting a hole-in-one with all your friends standing around. Blue Dog actually touched the goal cone with no camera, touched the cone and stopped. I couldn't believe it. It was crazy. Yeah. So that's the third highlight of my life.
Yeah. See, sometimes people get more complicated than they have to be. Because I know one of the things I did learn in robo games with like maze following robots, if you go into a maze, so if you're a person going into a maze, do one of two things: always turn right or always turn left. And if you always turn left or you always turn right, it may take you forever, but you will eventually get out of the maze or get to where you want in the maze. So a lot of people are writing all these really complicated mapping programs to do all this complicated stuff, but some people were just going as fast as they can, just following the walls, either always turning right, always turning left, following the walls. They always would complete the maze very quickly. So yeah, you can. Yeah, I did learn that in robo games. You can.
I think that's called the KISS strategy.
Yeah, I learned that in robo games. Sometimes you got great ideas, but they're just so complicated, they won't work. But yes, that's very cool. So yeah, kind of show off some of your robots, and then we can talk about your homebrew robots club.
Okay, hang on.
Sure. Actually,
got some tabletop robots here first. So if people are interested in starting off with robotics, I would do an Arduino. I like to use servos because they're relatively simple. Servos are 3 wires, 5 volt power, and a signal wire, and you pulse the signal wire 1 milliseconds, the wheel goes one direction, 2 milliseconds, it goes the other direction, and 1.5, it stops. I also like servos because you can scale up. You can build a tabletop robot, but then if you wanted to build a full-size robot, you can use electronic speed controllers to drive bigger motors, and you can still treat them like servos, where you pulse it 1 millisecond, it goes forward, 2 milliseconds, it goes reverse, and 1.5, it stops. And any speed between that, you're controlling the speed. There are cheaper ways to do it with H bridges and stuff like that, but time's the valuable thing. So here's a line following robot. I call him the snail. Then put him down and he basically follows the line. That's fun.
So what do you have, some infrared sensors for the line following?
Yeah, it's using infrared sensors. They're infrared sensors from Amazon. I think it's a company called Flying Fish. I've got these VTech my tape's rolling up here. Let me give them a little more width. I've got these VTech platforms, and they come with inexpensive Banggood geared motors. I've got some, it's just a small DC motor, gear motor, but I've got these 2-channel controller boards that allows you to treat those like servos too. I've got a lot of them. I bought about 50 of them, so I could sell the controller boards and the robot chassis. It's a robot chassis, about $12, and the controller board for $5. You've got my website. If somebody's interested, they can send me an email and we'll discuss it over PayPal. But this is the snail, and as you can see, he's going around them. Yeah, I like this chassis here. It's a round chassis. It's like a turtle. It's just kind of, Velcroed on there, and it's got a ball type caster wheel, patented popsicle stick technology here.
Right.
I like homebrewed style building with, popsicle sticks and hot glue and stuff like that. It's kind of an arts and crafts type building instead of engineering. Let me show you another line following robot.
Okay. See, one of the cool things about a lot of your robots is that they're not very expensive, and most people can afford them and put them together. They're just based on the Arduino or something similar.
Yeah. Come on, robot. Live demos, you gotta love them. Yeah, well, that's the fun of it, It's like, don't get hung up in not having just the right fastener, or just the right part. Build with what you have. I mean, there's always going to be limitations. This is not very good demo. Come on, come on, come on. There he goes. Okay, that's more better. That's a right-handed robot. This has got 4 of those flying fish sensors on the front. See if we can make it around here. Yay! He just needs.
Yeah, actually, I have noticed that sometimes your line following works better depending on what direction it's going.
Yeah, well, doesn't work one direction, try it the other direction. The Arduinos are great. You and I, Michael, we played around with the stamp microcontroller too, but everything's gone over to the Arduino. I like the Arduino, relatively easy to program. It's a C-like language, so whatever you learn with Arduino is applicable with the professional programming languages. A lot of semicolons and squiggly lines, right?
Right.
And then it's very interactive with the serial monitor. You can actually see what's going on with the pins and stuff. So for beginners, I recommend the Arduino. I recommend servos and infrared and ultrasonic. In fact,
I just wish the Arduino IDE was a little bit better.
well, it's not bad, okay? I mean, compared to like a PIC or something,
Yeah.
because, I played around with pick. Now here's, start of my book, Homebrewed Robots. I talk about the Arduino, and the first thing I want to do is you got with a servo 3 wires, power, red, the anodes, the power, the black is ground. And then you got your 1 signal wire that you plug into D0 through D13. And I plugged this one into D2, but the point is that you use a servo library command with the Arduino, and within an hour you've got a wheel going. Okay, so people that you understand programming for alphanumerics just having used computers all your life. Okay, if I want to make a database program, I make a program that asks the user for first name, last name, address, city, state, zip, and then I might print that out or sort it alphabetically or whatever. But how do you program to actuate a monitor or a motor? How do you program to actuate a motor? How do you program to monitor a sensor? Well, you basically need to wiggle a wire. You don't physically wiggle the wire. You send an electronic pulse down the wire that actuates the motor. And so here in the Arduino code, I'm basically pulsing this pin D2 so it moves this motor in a certain direction. Okay, how do you monitor a sensor? Well, the sensor I start off with is a little a snap action switch. There's all kinds of switches. There's rocker switches and toggle switches, but this snap action switch can be used as a bumper. And so with serial monitor in the Arduino integrated development environment, you can run serial monitor and you see that the status of the pin is a 1 until you depress it and it becomes a 0. And you let off and it's a 1. And you press it again and it's a 0. Now you put that together where I'm monitoring this pin, and as long as it's a 0, I run my motor. When the pin becomes a 1, I stop my motor. From here, you're on your way to adding 2 wheels, 2 snap action switches. When it bumps into something with the right switch, it backs up and turns left. When it bumps into something on the left switch, it backs up and turns right. You're on your way to building robots now.
Cool.
Let me show a few other tabletop robots. So again, at the Homebrew Robotics Club, which I've been part of for 20 years. By the way, this is a branch off the original Homebrew Computer Club of Apple fame. In 1984, when the Homebrew Computer Club disbanded because you didn't have to build your own computer anymore, there was a group that was interested in robotics. And the Homebrew Robotics Club is that same group 36 years later. And we're now online. We meet the last Wednesday every month. Our website's www.hbrobotics.org. Just Google Homebrew Robotics Club and you'll find it. Join our mailing list. But we meet virtually on Zoom the last Wednesday every month. And it's a great group. It also gives you a place to show off what you've built. We always have show and tell. So, nothing happens without a deadline. This is your deadline. Last Wednesday every month, you can come show off what you built. And so come have some fun with us at the Homebrew Robotics Club. So I'm going to show off some phase 1 table bots. A table bot, there's 3 phases. Phase 1 is it goes from one end of the table to the other and back. Phase 2 is it pushes a block off the edge of the table. And phase 3 is it pushes the block into a shoebox mounted at the end of the table. I'm going to show you a couple of phase 1, and then I've got a phase 2 robot also. This is using another VTech chassis that I've got. Like I say, if you're interested, go to my website, shoot me an email, and we can negotiate a price on them. I got a bunch of these things. It's a good little chassis to put an Arduino on, add some sensors. These are flying fish drop sensors. But, just build a robot, have some fun. This is a phase 1 tabletop robot. Basically goes from one end of the table to the other and back. We're hard to impress, but easily amused.
So what sensor are you using to keep it from going off the table?
What's that?
What sensor are you using to keep it from going off the table?
Oh, I'm using infrared.
Okay.
I'm using infrared sensors. Yeah. This is just, I think, a 6-inch plastic round with some servos glued to it, continuous rotation servos, 2 types of servos. We get servos from the radio control airplane world. Traditionally, they were 180 degrees for operating the flaps on airplanes. And back in the day, we had to modify them so they went 360 degrees. But now with the popularity of hobby robotics, you can buy a continuous rotation servo, for less than $15. So here's a couple of servos glued onto a 6-inch plastic round. I've got some continuous rotation, or they're continuous rotation servos. I got some servo wheels for them, but the continuous rotation servos you buy, they've got servo horns, and you can glue like jar lids or any toy wheel or anything you got onto those servo horns and make your own wheel. Don't wait for just the right part or bemoan that, oh, I can't afford the nice wheel like this or something. Just build with what you got. So I'm gluing popsicle sticks, and I've got some infrared sensors. These are actually from the Nito Bot Vac robot. And so let's see if this is again phase 1. He's just going to go back and forth without falling off the table, hopefully. A table bot is a robot that survives, lives, and plays on a table or pays the price. Now there is a phase 4 where it can actually fall off the table, but it needs to be able to, you need to put it back on the table. It still needs to be able to run. So actually you could achieve phase 4 before you achieve phase 1.
Right.
All right, let me go get a shoebox for a goal, and I'll attempt to demonstrate a level 3 table bot.
Okay, cool.
So there's the robot. Here's the block.
Looks like you got a sonic sensor, 2 sonic sensors, ultrasonic sensors, and infrared sensors. And he's looking for a box. Let's see. Arduino, ultrasonic, infrared.
I can't seem to locate my gaffer's tape, so I'm just going to hold this box here and we'll see how it does. It sees the chair. It wants to go for the chair. It thinks that's the block. This back a little bit.
There it goes.
Didn't quite get it in the box, but you get the idea. Let's try it one more time. We do the TableBot challenge not as a contest, but as a challenge at the Homebrew Club. Just for show and tell and just have fun with it. There aren't really any rules. We don't specify the size of the robot, the color of the table, the size of the box, or anything. Hey, that's more like it. I'll
Very
take.
cool.
Thank you very much. All right. Let's see here. You're back on the Zoom bot here. I let the computer ride on a robot. Actually, we did our wedding with this, so all my friends from California could log in and be at our wedding virtually. So I performed with a rock band, heavy metal, called Black Mask for about 8 years, I guess, 7 or 8 years. I've got I had well, I still got him back there, a crow, a couple skeletons, and a pirate named Rocky. And it was kind of like adult Chuck E. Cheese. So at this point, I'd like to share a video if that's okay.
That's fine.
Okay. Bear with me. So without any further ado, here is Black Mask from April in 2016.
Mhm. There's also a guy in Japan that has a robot band.
This is just like being in the bar. I can't hear you.
Yeah.
Who's that guy?
Yeah, like I was saying, there's also a guy in Japan that does something similar. He's got a robot band that he does.
That's Black Masked and the Black Masked Dancers.
Very cool.
Thank you. Hey, whoa, hang on. There we go. So, and I got a little piece of that right now if you want to have a look.
Sure.
All right. So this is Rocky. Rocky's a pirate. He's also a high five robot. He was always a big hit at Maker Faire.
Right.
Just radio control stuff though. A lot of fun. This is, you know, again, the servos that I was talking, whoa, the servos that I was talking about, you can, like if you do a tabletop robot, you can control bigger motors with servos or with electronic speed controls using the same, you know, pulse at 1 millisecond or 2 milliseconds. Ah. Yeah, yeah. Hang on a second. Let me close all that. Oh boy, I gotta get things back under control here. Now, Rocky, this one's fun, and this is fun for Halloween. This is just an inexpensive Halloween skeleton that I've put servos into. It's just standard, you know, $10 servos.
Right.
And you put you know, 2 in the shoulder, 2 in the thighs, and then you switch him on, and he dances. And of course, I put him on a base so I can move him around and stuff. Relatively simple project, and Halloween comes every year, so you know it's a lot of fun. I think this is probably 1, 2, 3. This is probably the 4th skeleton I've built. I built this one this year. So he's a new one. Sammy.
Very cool.
A couple of other robots that I've made. This is a robot from a book. Actually, I've had this robot for about 15 years. From a book, you may have seen him, Michael, Maker Faire. But there's a book where the kid builds this cardboard robot, right? And I've hacked it. It's a great kit. It's a great project because you just pop out the rivets and you put servos in here. So I put continuous rotation servos down here with the wheels and the standard servos up here with the arms. I've got an ultrasonics here, so when he senses a wall, he backs up and turns right. And this is wiring. He's low on power. Let me get a different battery in here. Hang on a second. Oh, maybe that's the problem. Hang on a second. Always be suspicious of power.
There he goes.
This one's Robbie. That's his brother. Fighting BattleBots. That's Robbie and Wiry. My little blue robot wired.
Very cool.
Yeah, like I say, that's by the same guy that made my little red toolbox. It's my little blue robot. And it's good for kids, you know, ages 6 and up, because they can build the cardboard robot and then you can hack it with 2 continuous rotation servos, 2 standard servos, and Arduino. Put some ultrasonics in there, and it's a great little project. All right. So next, we have Rodney Jr. Now this is a demonstration of machine intelligence. When I got started in robotics, it was from a book by David Heisman, How to Build Your Own Self-Programming Robot, wherein he described a machine or a robot named Rodney that you built from scratch with an 8085 microcontroller and control panel. And hang on a sec, I actually have that control panel. So this is the original control panel with most of the main board. And you basically set an address and 8-bit data, and you punch the load button and program it 1 bit at a time in binary. I've replicated Heiserman's machine intelligence theory with an Arduino and servos and a Roomba motion detector wheel, stall detector. Okay, and with Heiserman's theory, with a differential drive system, there are 9 possible motion patterns. Left wheel forward, left wheel reverse, right wheel forward, right wheel reverse, clockwise, counterclockwise, forward, reverse, and stop, okay? And so in level 1, the robot does random patterns until it discovers one that allows it to move. And the only 2 motion patterns with magnitude or displacement are forward and reverse. And in the beta, and this is currently a beta model, okay? When it's in a motion pattern and it discovers a successful response, the next time it's in that motion pattern, it tries the successful response. If it's still successful, it increments its confidence level. If not, it decrements its confidence level. The beta level has an element of memory where it remembers successful responses. Then in gamma, it generalizes those experiences. So it's in a motion pattern for which it has no high confidence level responses. It tries high confidence level responses from other motion patterns before reverting back to random. So when I switch the robot on, at first it's just going to do random motions, trying to discover one of the 2 motion patterns that give it displacement, forward and reverse. Basically, the robot's not happy unless this little wheel's spinning. When it's clockwise, counterclockwise, or one of the other wheels moving or it's stopped, this little wheel's not spinning. The only time this little caster wheel's spinning is when it's going forward or reverse. There's a little emitter detector pair back here that determines that. You've also got lights up here to tell you whether the robot's happy or not. When it's red, it's stalled. When it's green, it's happy, it's moving, okay? So when I first turn him on, he'll do random motions until he eventually discovers forward and reverse. It's not that the robot goes forward and reverse, it's that the robot learns to go forward and reverse, okay? Here we go. Let's give him another start. Machine intelligence demonstrations don't always work. Okay, there he goes. It's not that he's going forwards and backwards. It's that he learned to go forwards and backwards. All right. That's
Cool.
Rodney Jr. from How to Build Your Own Self-Programming Robot, but it's done on an Arduino instead of a homebrewed from scratch 8051 microcontroller board.
Right. Right.
All right. So from here, let's move into the 21st century and talk about ROS, Robot Operating System. ROS is the standard framework for robotics today. At its core, it's a publish and subscribe architecture, so that you could have a Raspberry Pi, a computer, and you could have various systems, and they talk to each other, okay? They also make drivers and packages for various bases and sensors and functions that so you can mix and match. There's a standardized package for mapping. There's a standardized package for path planning. There's a standardized package for visualization. And so you've got all of these tools, and it's open source. So that's the great thing. Plus, like I say, the community, this is the standard framework for robotics. I worked at Nito Robotics for 13 years. And the Nito robot is a consumer product, okay? It vacuums the floor. But the way it vacuums the floor is very intelligent. It uses a two-dimensional LiDAR. You can see the laser in there actually flashing. And so, you know, heretofore, the Roomba is just a bounce around robot. It does a combination spiral, wall follow, bounce around. Okay, I think I've finished, and it goes back to its docking base. The BotVac was the first really intelligent floor cleaning robot, where with the LiDAR, it could methodically vacuum your floor in a lawnmower pattern and know deterministically that it had completed the entire floor. The Nito BotVac has a micro USB socket in the dirt bin. Okay. And for years, I used to play around with it. Mike Ferguson came out with the original Nito package in 2010. And since then, in 2014, Mike, what's his name? Ralph Knock redid the package as the Nito package. And he uses launch files, which allow you to launch multiple nodes at the same time. Makes it easier, basically. But now you can drive around and create a map and click anywhere on the map, and the robot will autonomously navigate there. Let me get my other robots parked, and I'll demonstrate this.
Okay. So the cool thing about the vacuum cleaning robot, it's cheaper than a lot of ROS platforms.
Well, and if you have to justify it to somebody, it's a vacuum cleaner.
Right.
And then you get yourself a Raspberry Pi, and Ubiquity Robotics is the one that wrote the image that you put onto a micro SD card, and you boot it off of the Pi, and you SSH to it, secure shell. And then you're basically driving the robot around using a ROS utility called Teleop Twist. And you're using a ROS package called Gmapping, grid mapping, to create the map. Then you save your map, and you kill the grid map, and you load in what's called the navigation stack. The navigation, it'll load in the map that you just created. And it also includes localization, so you can see where the LiDAR scans touch the walls all around it. And there's a tool, visualizer tool called RViz, Ross Visualizer, that allows you to see the map and see your robot in the map. The little model of the robot's called a URDF, Universal Resource Description File. Robot URDF, Universal Robot Description File. The cool thing too is this can be used in a simulation environment called Gazebo. And so we're doing a lot of robot simulations in addition to doing the physical robot. So, you know, if you can't afford a physical robot, the simulation's another way to do it through Gazebo. Let me move this robot over here.
So do you program in C++ or Python?
Not really a programmer, Michael. I copy and paste.
Oh, okay.
But I'm able to modify C++ files, and I'm able to modify Python files. So it's like I got a Python file that's supposed to make the robot, or it's a C++ file in ROS that's supposed to make the robot navigate to a particular point in the map. And I modified it so it had like 5 points. And so I created a little program that it could go from one place to another, to another, another. It would basically follow waypoints. So, right. You know, I'm not really a programmer. I would say this though, I'm really studying Python. I think Python's the way to go. ROS 2 is very Python centric.
Yeah, that's what I've heard.
Yeah.
Somebody made a joke, and I've seen it in some over social media, that you prototype in Python, but you write your production code in C++. But I don't know if that's exactly true, because like you said, it looks like for ease of use, a lot of ROS 2 is going to be Python based.
Yeah, well, and relative to this, hang on a sec. Relative to this, see what's going on here.
So you've already created the map already for time. And basically what you did, you just drove the robot around so it could create a map.
Yeah.
And
so the first thing to do, and I've given you the GitHub for the ROS platform. But the first thing to do is you drive the robot around with this teleop twist program, teleop twist keyboard. Lets you drive the robot around and it creates a map. And I'm loading in the map here. So here's the map that we created earlier. I basically drove the robot around and we created this map. Okay, and then I saved the map, and there you can see the maybe you can see it. Oh, here it is. You can see the robot over here. You can see the LiDAR scans where it's darker. That's called the local cost map. If you looked all around, you'd see a wider blue area. You'll see like a blue surrounding the whole map. That's the global cost map. The cost map has inflation barriers that determine how close the robot can get to the walls, and that's adjustable through the ROS parameters. But now I'm going to come up here and click on 2D nav goal. And then I come out here and I point and I press and I drag. You see the arrow there, whatever direction I want the robot facing, that's called its pose. And you can see the model of the robot navigating to that spot on the map that we've created. It looks a little delocalized there.
so like we talked about, this is not really, this is kind of the discussion I've had with other people. This is not really SLAM. This is more localization.
Well, this is navigation.
Yeah.
Okay. And so the navigation is, loading in the map,
Right.
and you can't really see it, but there's a green line there. That's the path following.
Right.
Move base in Ross. And my robot's a little delocalized. He's going to get localized here in a bit though. But all this is 3-dimensional, so it's really nice. Let me click on the 2D nav goal here and try to get him into a goal that's not behind the dresser there. But here you can see the robot in the physical world navigating to that place autonomously. And so now it's at that goal, okay? And I can tell he's localized now because all my scans are up against the wall and stuff like that. So let's get on the Zoom bot here. Okay. And I've got my map of the house here.
Right.
Okay. And I'm going to set a goal. So I click on 2D nav and point, press, and drag here in the kitchen. And the robot's autonomously navigating there. And it'll be facing the way that I told it to face. So I'll go to my navigation screen terminal, and it's reached that goal reached. Okay. I'm going to set another goal here in the hallway. Point, press, drag, mouse up. There's a path planning line, and the robot's physically going to that goal.
So is your laptop running Ubuntu?
Yeah, it's Ubuntu.
And you're SSHing into the robot, correct?
Yeah, you SSH to the robot. I run the base program on the robot, and I do the mapping and navigation on the workstation.
Okay. Are you running a Pi 3 or Pi 4?
It's a Pi 3. So this is he's got to the second point of the map. Let's make this map a little smaller. Here it goes. Let's get a third waypoint here. Point, press, drag, mouse up, and I've got path planning lines now where the robot's navigating to the third point.
I think I may be wrong, but I think iRobot is doing something similar to this now because they actually have an app that shows you the map of your room or your house or
It's
your apartment?
navigating with a camera. They don't have a LiDAR. But yes, they're actually doing navigation now, logical navigation, so they can do the lawnmower pattern instead of randomly bouncing around. Yes, iRobot now is making intelligent robots. In fact, they're making a D-shaped robot now, which is an indication that Nito's done things right. But theirs doesn't have a LiDAR. They use a camera to navigate with.
Yeah, I think they're using some kind of version of Base Slam, Visual Slam.
Yeah, oh yeah, yeah. Well, you can do SLAM with a camera, yeah. Okay, and so now let's get our fourth waypoint. Okay, I'm gonna 2D nav goal and send the robot to a fourth data point. Okay, I've got my path planning lines. I've got my path planning lines going there, and you can see the little model of the robots navigating to the fourth waypoint. Go to many colors. Okay, so this is our fourth waypoint, and I'm going to set him the final waypoint there in the computer room. (2D nav goal, point, press and drag, mouse up, and the robot will now navigate there. So it should reach that data point, and it'll turn around because I set the pose in the opposite direction. You see it turning around.
Right.
And it has reached its goal. So that's the Nito robot. We did a map, we saved the map, and we loaded the map in, and there you see it navigating. We've just recently gotten this code. We've got part of it moved over to ROS 2. ROS 2 has some interesting features, not the least of which with ROS 1, there's this concept known as the master. And basically master links up all the subscribers with the publishers. But ROS 2 is masterless, so everything runs in parallel. Right, with this, if the master died for some reason, you'd have to spin up a new master and then restart all your subscribers. It's kind of interesting with ROS 2, if the master crashed or died, you can just spin up the master again and all the subscribers are still there and they come back online, so that's nice. Also, the navigation is quite a bit more sophisticated, where it has features that you can do waypoint, you can follow waypoints automatically, and it has dynamic following, so it could have it follow you. You've also got plugins, so at your various waypoints, you could maybe take a picture or, I don't know, make a sound or something like that. You could also incorporate recovery behaviors. The nav 2 is more sophisticated. So it's very interesting. Lastly, like I say, I'm writing a book and it'll be called Homebrewed Robots. I hope to have it out this summer. Basically, in addition to telling my Silicon Valley story, it'll have 5 project chapters. The first one's going to be the Tablebot. The second one's going to be machine intelligence, where I described the Rodney Jr. The third is going to be Robo Magellan, where I describe how to build a Robo Magellan robot. Then the Nito Turtle, where I basically describe this using a bot vac and mapping and navigating with just the bot vac. And the last chapter is going to be something called the smart table. And this is where I'm going with everything. Is it'll be like a tray table. You know, the original Turtlebot stands like 2.5 feet tall, and it makes a nice little table. I use it as a table to put my computer on, and I do Zoom, and I have the robot carry the computer around for me. But the idea of the smart table is a table that can reliably get from one place to another and back again in an unstructured environment. I think that would be useful. This is not perfect. It can't navigate doors. It can't navigate stairs, but it could wait at a door until the door's open. Okay. And it's a human assisted robot where you can put things on it and send it to the bedroom or send it to the kitchen or send it to the living room. Carl, who's not getting around too well, can put his glasses and his smartphone, and a snack on it and have it follow him, from the kitchen into the bedroom or something like that. Even in a small business, you need to take something over to John's cube. You could put it on the smart table and it navigates to that cube. And then you've got a camera on there. You can see whether or not John's there. If John's not there, you could, drive over to the other cube and ask Sandra if she'll put that widget on John's desk, something like that. So the smart table is a tray table that can reliably get from one place to another and back again in an unstructured environment. I think I have a little demo here. Hang on. See if it's out there. Are you out there? Hang on a second.
Yeah, so there's a lot of people developing robots very similar to what you're talking about for assistants, butlers, waitresses, waiters, busboys, mail robots. Mailroom robots.
Well,
supply robots. Yeah.
with
AMRs.
the Turtlebot, I think they've taken a step backwards. And I get it, you got to make money at this thing, but the Turtlebot is the standard trainer for Ross, okay? And used to, the Turtlebot was built on a Create, and it used the Connect, but it's sized enough that it could actually do some work, carry a payload. Now, the Turtlebot 3 is a tabletop robot, and it's just an educational device. And, I feel like the original Turtlebot platform really hasn't been fully exploited. I want a full-size robot that I actually do something with. And so, you look at the bot vac or you look at a Create and you get yourself some 12-inch diameter, 1/8-inch rounds and the right standoffs. I would use a Astrea 3D camera or an Intel RealSense or something like that to cover the top part so it doesn't navigate under tables and under couches. But, I really like the original Turtlebot form factor. And so I've got one over here. Let me log in and I'll bring him over.
they're like Robotics is Turtlebot 3. That's more of an educational introduction to ROS robot.
Well, see, the original Turtlebot, and one time at the Homebrew Club, we had a Ross roundtable with real heavyweights. Mike Ferguson, Anthony Procanis, Melanie Wise. And I asked them, you know, why the Turtlebot wasn't as popular, you know, as why the Turtlebot wasn't as popular as it could have been. I almost got booed out of there, but you know, because it was actually successful, it was popular, but you know, I don't think they gave it the full effort to really promote it. And the response was that they were really told not to pay attention to it, to focus on the PR2. You know, ROS was built on the PR2, Personal Robot 2. It's a $400,000 robot research platform for universities. Its claims to fame is it could actually fetch a beer from the refrigerator. It could plug itself in. It could even fold clothes. Okay. But, you know, they really didn't do the hobbyist type stuff. And again, I keep coming back to, you know, I think that, I think there's still space there. I think people want, you know, the original Turtlebot.
Yeah, so that,
And I call it the smart table.
right. So you dropped a lot of names there. Of course, people don't know. You basically dropped the names of the people who were at was it Willow Garage?
Yeah, these are your original Willow Garage interns. And
Right.
by the way, there's a fantastic film out there by Red Hat Productions called How to Start a Robot Revolution, and it's the story of Ross. And it's really a good film. Let's see here, bear with me. I need to save this.
So the PR2 was a really expensive research and development robot. And for many reasons, it never really took off. And that was kind of spelled the end of Willow Garage. I think a lot of those.
Well, Willow Garage had its time and place, and it was successful. What Scott Hussein wanted to do was to create a framework.
Right.
And he did. And it's, you know, it's success, you know, to this day with Savvy Oak and Fetch, you know, and Ubiquity and other robots, you know, that are still being created. Now here's my smart table here. Okay.
Right.
But that's basically the Nito bot vac with a, that's the Nito bot vac with a Turtlebot superstructure on top. And I've got ultrasonics there connected to an Arduino, and with raw serial, it pipes it into the same master as the bot vac. So let me load in my RViz here, my ROS visualizer.
So a lot of people are taking this platform or their version of this platform. There's been a lot of talk and work on in the last few months on, so they basically take this, what you call your table, and they attach different stuff to it. The latest cool stuff is they're attaching UVC lamps and disinfectant defoggers.
Exactly.
And make it a tall stack robot that can help with the COVID pandemic.
Yeah, well, and we talked about this, Michael. Hate to say it, but COVID's really been an accelerator for robotics. Now people want to be places without being places. And so, you know, I think it's accelerated robotics, you know, 5 or 6 years.
Right.
Let me get this robot right. There we go. Okay, hang on. I've got one more thing to show you here. Oh, I need to turn on the ultrasonics. Bear with me.
Um,
Okay. So here you can see, maybe you can, the, might have to send you an image of it. But you can see the cones from the ultrasonics coming out the front of it here.
oh, yeah, yeah, yeah.
Oops. Bear with me. Okay, so here you can see the ultrasonic cones coming off the bot vac, right? And if I put my hand here, you can see that it's detecting the distance. So that keeps it from navigating under the couch and under the furniture.
Right.
So that's a range sensor, that's ultrasonics. And again, what I've done there is the bot vac, which has the LiDAR, I'm able to map and navigate with, and then I've appended it with a Turtlebot superstructure, and then I've added ultrasonics to that to keep it from navigating under the bed and the couch. And this is what I call the smart table, and it's basically a table that can reliably get from one place to another and back again in an unstructured environment. So when I'm writing my book, Homebrew Robots, it's basically 5 project chapters. The first is going to be the table bot, robot that survives, lives, and plays on a table or pays the price. Machine intelligence with 3 levels of machine intelligence, random, memory, and generalization. Robo Magellan, where you're interfaced to a GPS, and if your target latitude's higher than your actual, you go north. Your target longitude's higher than your actual, you travel east. The Nido turtle, which is the basic turtle with ROS, mapping and navigating. And then finally, the smart table, which will be a tray table that can reliably get from one place to another and back again in an unstructured environment. And hopefully I'll have that out in this summer. So folks that are interested in this kind of stuff, go to the Homebrew Robotics Club website, hbrobotics.org. And we meet the last Wednesday every month on Zoom, so you can join in on our meetings. We always have show and tell, so you can show off your robot and join our mailing list at hbrobotics.org.
Right.
And let's build homebrewed robots.
Very cool.
All right, very good.
Okay. So thanks for showing off your robots and spending some time with me.
We had
Let's
some.
say goodbye to everybody.
All right.
And we'll see you next time on the next video.
All right. Sounds good, Michael.